This next example is going to be tougher because they're not going to give us the function that we need to optimize. We'll have to come up with it ourselves, and then, very important, we also have to figure out what the domain of that function is. So here we go. A farmer wants to fence an area of 15,000 square feet in a rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. How can he do this so as to minimize the amount of fencing? Okay, so he wants to fence in a rectangular field whose area, I'll just call that A, whose area is 15,000 square feet. The thing we want to optimize, the function we need to set up to optimize, is in this question. How can he do this so as to minimize the amount of fencing? Amount of fencing, that's the function we need. We need an amount of fencing function, and then we'll be looking for the minimal value of that. Now we know that area of a rectangle is length times width, so let's put in a couple of variables to represent that. And so now we know that x times y is 15,000. But there's one other thing in this problem. He wants to divide it in half with a fence parallel to one of the sides of the rectangle. And you can do this however you want. You could do it like that, or you could do it like this. It doesn't matter. You'll get the same answer either way. But I'm going to do it like that. So notice this length is also x, and this length is also x. And then the horizontal width is our y. So what's the amount of fencing? All that, I'll call that capital F for fencing. The amount is, well, there's 3 of those x lengths plus 2 of those y lengths. Now, we have a problem here, though, and that is that we have 2 variables in our function. Because all our differentiation rules only apply to one variable, all our optimization stuff applies to just one variable, so we need to have just one variable in our function. Fortunately, this extra bit of information that we haven't really done much with yet, that allows us to express one variable in terms of the other. So if I solve this, so if I take this 15,000 equals xy, and I solve that for, let's solve it for y. Again, it doesn't matter which variable you pick, but I'm going to choose to solve for y. So y is 15,000 over x. I can put that expression in for y in my function, and now I have a function of just one variable, so I'll call that f of x. 3x plus 2 times 15,000 over x. In other words, the function we're dealing with is 3x plus 30,000, and I'm going to call that x to the negative 1 because we'll be differentiating pretty soon, and I want differentiation-friendly format for my function. Next, and crucially, we need to figure out the domain of our function. Without the domain, we don't know how to proceed. If our domain is a closed interval, we can use the closed interval method like we did in the last example, but in that case we need to know the endpoints of our closed interval. And maybe our domain won't be a closed interval. In that case, we can't use the closed interval method and we'll have to make a sign chart. So let's think about what our domain is. What's the smallest? Let me put over here, we need domain. Again, that's critical because that determines how we're going to proceed. Okay, so what's the smallest x could be? So here I'm determining the domain. Well, certainly x can't be negative. Because x is a length, and length can't be negative. X also can't be 0, because if x were 0, then the area we were enclosing would be 0. Right? If you look at our area function, if x is 0, x times y is going to be 0, and so that's not going to be 15,000 like we need it to be. Okay, so x has to be a positive number, not 0. What's the smallest it could be? Well, could x be 1? Sure. If x was 1, then the width of our field would be, and here I'm looking at the formula we have for y, which is 15,000 over x. So y would be 15,000 over 1, in other words, 15,000 feet. Now, this would not be a practical size for the field. Who would make a field that was 1 by 15,000? But mathematically, it could happen. Could x be a half a foot? Yes, it could be. If x was half a foot, y would be 15,000 divided by 1/2, which would be 30,000. So mathematically speaking, you could make a field that was only half a foot wide and 30,000 feet long. Again, that wouldn't be practical, but in the mathematical sense, it could happen. Let's look at one more. Could x be 1/100th of a foot long? Yes, it could be. Because then y would just have to be 15,000 divided by 1 over 100, which would be, let's see, that would be 15,000 times 100. So that's going to be 15,000 with 2 more zeros. So that's 1,500,000 feet. Again, that would be a crazy way to make a field. I mean, you wouldn't have cows or a row of vegetables or whatever that's only 100th of a foot wide. That'd be like, what, 1/10 of an inch. But here's the thing. We don't know in a practical sense what is the smallest value x could be. We don't have that information. And so we have no way of knowing what x value is too small, what x value can we roll out. So all we can say is that x has to be some positive number, and as far as we know, it could be a teeny tiny fraction. So all this tells us is that x is just some positive number. Now, what is the biggest x could be? Could it be 15,000? And you'd have a field that looked like this, and your y would be 15,000 over x, so that's 15,000 over 15,000. So y would be 1 foot. Again, this would be a crazy way to make a field, but mathematically speaking, it could happen. Could x be 60,000? Sure, that could happen. Then you'd have a super skinny field, and your y would have to be 15,000 divided by 60,000, which is 1/4. So if x was 60,000, you could make a field like that, or let me say it this way, you could make a rectangle like that by making y 1/4 of a foot, so 3 inches. Again, that would be a crazy way to make a field. In real life, it wouldn't work. But again, we don't know what the practical limitations on the field are. We don't know what's the smallest y could be, and so we don't know what the biggest x could be either. So at this point, x can be any positive number, no matter how large. So our domain then is 0 to infinity, not including 0. Again, in real life, this wouldn't make sense, but we don't know what the limitations are in real life, so we have to go with what can be done with rectangles mathematically. Notice this is not a closed interval. It doesn't have 2 endpoints that it contains. So we cannot use the closed interval method. What are we going to do instead? Instead, we'll make a sign chart. So we'll do that and finish the problem in the next video.